So welcome back students. This is the part 2 video of the revision of unit 1. So in this particular video we'll be discussing the remaining topics from unit 1 which are important. So we'll start with the voltage division rule today. So as I have told you in the previous class also, that if suppose we are having resistors in series, so in that case the current is going to remain same. So if we talk about the value of I, the value of I will be same, but the value of the voltage will be different. So I will be remaining same and voltage will be varied, and they will vary as per the formulas that are being provided here. And this formula simply tells that if we want to find voltage across any resistor, that is equal to simply total voltage divided by total resistance, which is the R1 plus R2, into resistance across which we want to find the voltage. Suppose in this particular figure, if we want to find the voltage across V1, so it will be total voltage by total resistance into R1 itself. Similarly, if it is V2, then it will be total voltage by total resistance into R2. Means subscripts being used are same and same. Now based on this you can see the kind of question that can come. Suppose we are being asked to find values of V1, V2 and V3. So what we can do, V1 is simply the total voltage. First of all, total voltage is given 12, and total resistance means R1 plus R2 plus R3, that is equal to 8. Now we will multiply it with the resistance across which we want to find the voltage. So V1 is across R1 value is 4. So we will write it like this. So it is 48 upon 8, that is equal to 6 volt. Now we will find V2. V2 is again 12, total voltage, total resistance is 8, into resistance here is 3. So it will be what? 4 into 2, 4 into 3. So it is 9 upon 2, that is 4.5 volt. Now we can see that option D is the right option, but still we will do V3 also. So it will be 12 upon 8 into the voltage across, the resistance across V3, that is 1. So it will be 4 into 2, 4 into 3. So it is 3 upon 2, that gives you 1.5 volt. So in this way we can use the voltage division formula to calculate the voltages across the resistors. In the same way we have a current division rule also. So in current division rule, what we will be having is resistors in parallel. So we are having here resistors in parallel. So if resistors are in parallel, then voltage remains same. So the voltage does not vary, but current will change. Now according to what formula? The formulas are given here. Okay, we have derived these formulas in the class lectures in the offline mode, so you can refer to those notes. Now here I will directly tell you how to remember the formula. It tells us that if we want to find current across any resistor, that is equal to the total current divided by total resistance, which is again like R1 plus R2 kind of thing, into resistance of other branch. So last time it was what? It was voltage divided by R1 plus R2 into resistance of same branch, but it is the other branch. So you can see here, if we have to find the current across I1, we are using subscript R2. Means this current I1 we are calculating across R1, but in formula we are using the other value, that is R2. In the same way, if we are finding I2, we are using the R1 value at that time. You see one question based on it, so that you will get to know how to use it. Suppose we have to find I1 value and we have to also find the I2 value. So first of all we write total current by total resistance. So total current is 5 and total resistance means R1 plus R2 is 25. So this thing is common in both the currents. Now we have to write here the value of the resistance. So for I1, if you see, if we are finding the I1, the other value resistance is this value, which is 20 kilo ohm. And if we are finding I2, then the other value of R is this 5 kilo ohm. Right, so it is 100 upon 25, that gives you 4 ampere, and this is 25 upon 25, that is 1 ampere. So the answer is 4 ampere and 1 ampere. So option number C is correct. Now we come to the very important topic of this particular unit 1, that is Thevenin theorem. So basically we will cover two important theorems. One is Thevenin, other one is Norton. The concept in both the theorems is that if suppose we are having a network where some part of the network is a fixed one and some part of the network is a variable one. Suppose in this example we are having a circuit and we are the terminals where some load resistor is connected, RL. Now the value of this RL is variable, means it can be suppose 50 ohm, it can be 100 ohm, it can be 200 ohm, it can be any value as per the requirement of RL. While as the rest of the circuit, suppose their values are like this much, so this value is not changing at all. So what we are realizing here is we are having two type of values here, right? One is the value which is here, it is a fixed value, so it is a fixed network, and we are having this part of the network which is variable, right? So that is what is given in the first statement. We will be having certain element, certain kind of network where some part is variable, suppose the load network, and some elements are fixed. So in that case we will be using Thevenin theorem. So according to the Thevenin theorem, what we can do, we can replace the fixed part of the network with the equivalent circuit, and that equivalent circuit is the circuit that was given by the Thevenin. Now let us see what was the statement of the Thevenin theorem. So according to the Thevenin theorem, if suppose you are having any kind of linear two terminal circuit, the circuit must be linear, having resistors and all that follow Ohm's law, then it should be having a two terminal circuit, means there are suppose two terminals here A and B, across which we can connect any given load. Then we can replace the fixed part of that network with one circuit that consists of VTH in series with RTH. Okay, we are having voltage source VTH in series with the resistor RTH. Now we have to understand what is our VTH, what is RTH, and how to find it. That is also given in the statement itself, that VTH is the open circuit voltage, right? VTH is the open circuit voltage. So we are defining VTH as the open circuit voltage across the load terminals. And what is RTH? RTH is being defined as the equivalent resistance across the terminals, or you can say across the load. And there's a condition while we find RTH, that is independent sources must be turned off. Now in the previous classes we had a discussion regarding independent sources and dependent sources. I told you there, as far as the independent sources are concerned, they are of two types, right? What are those two types? It can be an independent voltage source, or it can be an independent current source. So they must be turned off. Turned off means they must be replaced by their equivalent internal resistances, which actually means if there is a voltage source, it must be shorted, because the internal resistance of voltage source is 0, and if it is a current source, it must be replaced with open circuit, because the internal resistance of current source is infinity. So this is the definition of Thevenin theorem, and the same thing is given in the slides which are being provided here. Now ultimately, once we will be finding the VTH and RTH, then we can connect any kind of load that is being given in the circuit, and we can find the value of IL. Now what is interesting in this part of Thevenin is, according to the Thevenin, if we are having any kind of a normal network with a fixed part and a variable part, and we replace that same network with Thevenin circuit consisting of VTH, RTH, and we connect the same load here also, and now we are trying to find the current across the load. According to the Thevenin, the current IL we get here in the normal circuit, and the current IL we get in this equivalent circuit, they will be exactly same. This is what the students must have tried in the practical also, practical number 2, where they were using the Thevenin theorem verification that current in both the cases will be the same. So in this circuit, if we have to find the current, we can simply use the formula VTH divided by RTH plus RL, because these two resistors are in series in this circuit. Now you see, we will be applying the concepts on the given question. Suppose the question is we need to find the Thevenin voltage across the load. So load is A and B, so across A and B 24 ohm is connected. So this is my load resistor, you can say. So what is the definition? Thevenin voltage is calculated as open circuit voltage across the load terminal. So what we need to do in the given connection is we need to remove this 24 ohm resistor. So once we remove it, so this is my VTH voltage, which is equal to the open circuit voltage. And because this point and this point is same, this point and this point is same, so we can say the voltage across this resistor is also VTH. Now it becomes an easy problem, because the current that will be coming from this 10 volt will be reaching here, and after this it will directly go to 12. It will not go across this path, simply because we are having here open circuit, right? The circuit is open here, so there will be no current. Now this 2 and this 12, they are in series because the current is flowing in 12 only. So what is I value then? What is I value then? I is V by R, which is 10 over 14. And what is voltage across 12 ohm? It is I into R, that is 10 upon 14 into R value, that is 12. So it is 120 upon 14, that is 60 upon 7. So this value will come out to be 8.5. So the right option is B. Similarly, in the same question, suppose we have to find the RTH. Now again I will repeat, RTH is nothing but the equivalent resistance that we can find across the load, with the condition that if we are having a voltage source, that must be shorted, and if we are having a current source, that must be open circuited. Okay, provided they are independent sources. Now this is a 10 volt, it is a voltage source independent, so we can replace this with a short, and then let us see what will be the circuit. And one more step we have to follow while finding RTH is we have to open the load. We have to open the load. So considering all these steps, this equivalent diagram can be something like this, right? Then A and B, load has been removed, so this is my R equivalent as RTH, right? Now see students, these two are in parallel, so 12 parallel 2 will be your RTH. So this value should come around 1.7 ohm. So with these two basic questions, we understood how to calculate the VTH, how to calculate the RTH. Now we will do one very broad question where we have to find again the VTH, the RTH, the equivalent circuit. So these things we need to find out in this particular question. Now what we can do is, first of all, we can find the RTH value, because calculation of RTH is easier. So we can start with the RTH calculation. So we can write like this: RTH calculation, and again, like we did in this particular question, we will be following the same steps here also. So we are having a voltage source, so voltage source has to be shorted in this case if we are finding RTH, and we are having a current source also, it must be open circuited while finding the RTH value. Okay, so equivalent circuit would be something like this. It would be something like this. So this has to be open circuited current source, then we are having this one. Then what about the load? Load also must be open. Okay, these steps are given here also. Load must be open means you have to remove the load. Now this will be your RTH value. Now values are given 4, 12 and 1. So you can see students, these two are in parallel. So 4 parallel 12 will be how much? 48 by 16, that is 3. Now that 3 and this one are in series. 4 and 12 were in parallel, so 3 and 1 will make it 4 ohm. So we can say RTH is nothing but 4 ohm. Now we will find the value of VTH. Now when we are finding the VTH, we have to just follow one step, that is open the load. Then the rest of the circuit will remain same. So let us draw the circuit first. So we have a current source here, then we have a resistance, and we have to find the VTH. We have to open the load, so this will be my VTH across these 2 points. Now what is important to understand here is that the current in this 1 ohm is not possible because it is an open circuit over here, so no current will flow here. It means there is no drop. When it is an open circuit, it means no drop. So we can say that the potential of VTH will exist here also. So this point is also VTH only. It means this point is also VTH only, right? Then we are going to do this question using nodal analysis. So we will assume certain currents first of all before we proceed further. So let us assume that this current is I1 and this current is I2. So we'll be assuming the current directions as per our own choice, and now we are ready to write down the KCL equation. So we can write 32 minus VTH upon 4, because it is V by R. You can either write I or V by R, is equal to I2. That will be what? VTH upon 12. This is the leaving current, and if you see the 2 ampere, it is also entering a node because it cannot move towards right. It is an open circuit over here, so it will move towards left only, right? So this 2 ampere is also entering, right? So we have to write it on this side. So 2 plus this value will be VTH by 12. Now what we need to do is just solve it a little bit. So once you will be solving this equation, because we have only one unknown, you will get VTH value equal to 30 volt. Okay, you can try this by yourself. So since we got VTH also, RTH also in the previous slide, so we are ready for the Thevenin equivalent circuit. Okay, so my Thevenin equivalent circuit I will draw here. It will be VTH, RTH, and in series with one load resistor, that is RL here. Okay, so RTH value is 4, VTH value is 30. Now see students, in order to find the load current across these 3 different values, we can write that value of IL is equal to VTH divided by RTH plus RL. Okay, and the same formula will be applied for second part also and the third part also. Now see, VTH value is fixed, RTH value is fixed. What is changing is the RL value. For part A, the value is 6. For part P, the RL is 16. Okay, this is 16, and for third part, the value of RL is 36. So you can see students, first value is 30 upon 10. So IL in part A is how much? It is 3 ampere. For part 2, it is 30 over 20, 30 by 20, that is 1.5. And for third part, it is 30 upon 40, that is 0.75. So the point is, we are able to find all the values of load current within one step only, and this was made possible because of the Thevenin theorem that we applied. And this is the advantage of Thevenin, that if the value of the load is variable, you can find still all the values within one go. Then the next important theorem is Norton Theorem. In the Norton Theorem, it is very much similar to the Thevenin Theorem, that tells again that if we are having any kind of linear circuit, then that can be converted into a current source, that is Norton current, in parallel with the resistor, that is Norton resistance, and then again we can connect the RL. Now let us see the statement. So the Norton theorem was given 43 years after the Thevenin was published, and according to this statement also, if we are having any kind of linear 2-terminal circuit, that can be replaced by an equivalent circuit having Norton current source I Norton in parallel with the resistance R Norton. So this is where the difference lies. In the Thevenin theorem, we had VTH, that is the voltage source, in series with resistor RTH, and here we are saying it is the current source in parallel with the Norton resistance Rn. Now, how to find I Norton, how to find R Norton, that is also given in the statement, that I Norton is nothing but the short circuit current. It is the short circuit current across the load terminal. So IN has been defined as what? Short circuit current across the load. And R Norton is simply same as RTH. So there is nothing new in it. So you can see here there is a comparison given also. How are the two theorems different? In Thevenin we talk about VTH in series with RTH, and here we talk about I Norton in parallel with R Norton. RTH and R Norton, they are exactly same. VTH is the open circuit voltage across the load, while as Norton current is the short circuit current across the load. Okay, this is the difference. Now we can directly move on to the question to understand how the things work in a Norton theorem. Here also we will again find first of all Norton current, then we will find the Norton resistance also. So how to find Norton current? For that we have to use the step short the load. So what we will do in the diagram, we will copy the diagram and once again. So we have here the values. Okay, this is a diagram. Now if we talk about the terminals A and B, we have to short the load, means we have to do the short like this. Now what happens is the interesting part. When this is shorted, now you can see that the two resistors are coming in parallel. Now what are the two resistors coming in parallel? These two resistors. Now when the resistors are in parallel and this is a short circuit, in the short circuit resistance becomes 0. So 0 and this 6 are in parallel, so equivalent will be also 0. So this circuit can be reduced to a simple network having a voltage source, having a resistance, a current source and a short like this. Right, this is the Norton current, I Norton. This is 4, this is 3, this is 3, this is 15. Now in this circuit we have to find the Norton current. Now how will we do it? We can use the concept of again nodal analysis, and we will assume here some voltage Vx. So we can write assuming these as the current directions. So we can write 15 minus Vx upon 3, it is the entering current, 4 is also entering current, and Vx upon 3 is the leaving current. Now we can solve it. We can write 15 minus Vx plus 12 equal to Vx, okay, because we'll take 3 as LCM and then 3 and 3 can go also, okay, later on. So solving this, what we will get? Vx as 27 upon 2 volt. But our ultimate aim is to find I Norton, okay. So we can say I Norton is nothing but Vx upon 3, which is 27 by 2 upon 3, which is 27 by 6, that is 3 into 9, 3 into 2, which is 4.5 ampere. So we got the value of Norton current as 4.5 ampere. Now is the time to find the R Norton value, okay, R Norton. So R Norton is easy. We have to open the load that is already open, we have to open the current source also, and we have to short the voltage source as well. So our circuit would be something like this. Let us remove the extra lines and all. So what will be our circuit? This is shorted voltage source, then we have 3, then we have open circuit current source, then we have again 3, then again 6, and then across the load terminals we are having R Norton. Now you can see, students, these two resistors 3 and 3, they are in series, that is 6. Now this 6 we get here and 6 over here, they are in parallel, so again the answer is 3 ohm. So R Norton is 3 ohm. So we can find the Norton equivalent circuit, means a circuit having Norton current in parallel with R Norton, and both the values we have calculated. I Norton we got in the previous slide, it was 4.5 ampere, so we will write here 4.5 ampere, and R Norton we got just here 3 ohm. So this is the equivalent circuit, okay, Norton equivalent circuit. So that's it in this video regarding Thevenin and Norton. Now the last thing we will be covering here is the AC analysis also. Now we have covered this in the classes also, that how AC was advantageous over the DC, and the main problem in DC was that, like, Edison was unable to supply the DC to the longer distances. As a result, he could only supply electricity to those places which are very closer to the transformers that he was having that time. But once we had an advent of an AC, then it was possible to transfer it to the longer distances, because there are very less I square into R losses, and we had a transformer also where we could have step up and step down the voltages, and that made it possible that we could supply AC to a larger distances. Then there are a few basic points, like DC flows only in one direction, while as AC flows in the alternate directions. Okay, there is a positive half, there is a negative half also. Then similarly, if we see the plot, then the plot of the DC will be always constant, so it always remains constant ideally with respect to time. But when we talk about the AC analysis, so we have the positive half, we have the negative half, so it continuously varies with respect to time. It can have minimum value, maximum value, and so on, any value it can assume. Then there is no concept of frequency in DC, it will always be 0, while as if we speak about the alternating currents, we have a concept of the frequency as well. Suppose in India we say that frequency of the AC coming at our homes is 50 Hertz. That means in one particular second, in 1 second, the alternating cycle that we are having, this is being repeated how many times? 50 times. Alright, so we have a concept of frequency as well. Now there are certain very basic terminologies that a person should be aware of once we talk about the AC analysis. So we will discuss all the basic terminologies one by one in the upcoming slides. So we are starting with the amplitude. What is the amplitude? Now amplitude is nothing but, if you see the diagram, it is the maximum value. Okay, if you see in this diagram, we have a value here which is the maximum value. Similarly, we have maximum value in the positive half, we have a maximum value in the negative half. So both are called as amplitudes, and the difference between these 2 points is called as peak to peak value. Amplitude is also referred as the peak value also. Then we have the instantaneous value. Now instantaneous value means we are looking at the value at any instant of time. Right, suppose I can ask what is the value at t equal to 1, t equal to 3, t equal to 5. So we can say that there are different values of the voltage, right? That will be instantaneous value. Then we have the concept of frequency that we discussed. Frequency means number of cycles covered in 1 second. Suppose you can see in figure A, we have 1 second. In 1 second we have only one cycle of the sinusoid, so the frequency will be 1 Hertz. Here you can see in 1 second there are 2 cycles being covered, so it will be 2 Hertz. Similarly, suppose we say that USA is working at a frequency of 60 Hertz. That means in 1 second the sinusoidal signal is repeating itself 60 times. Then we have a time period. Time period is the total time taken to complete one cycle, and time period is given as 1 upon frequency. It is the inverse of frequency. Then we have a concept that once we define the angle, in a sinusoid, we can define that in radians or we can define that in degrees also. Suppose we have 90, 180, 270, 360 degrees, or we can have in pi by 2, pi, and so on. Now sometimes we might have to convert the things from radian to degree, degree to radian, as we shall see in one of the questions, one of the numericals. So we can use the formulas accordingly. Okay, so here we can say that the value of 2 pi is same as the 360 radian. Okay, accordingly we can use the formula. Then we have the angular frequency also, which is omega, and we define omega as 2 pi f or also 2 pi upon t. Then when we talk about the voltage and the currents, they may be in phase or they may not be in phase. Suppose if we see in figure 1, what is happening? The value of 0, the value of peak in positive half, the value of peak in the negative half for voltage and current, everything is happening at the same instant of time. So that means they are in phase. But if we look at figure 2, in figure 2 you can see that the current is starting earlier than the voltage, isn't it? So you can see here, the moment voltage is starting at this point, the current has already reached it to certain value. So current is leading in this case. Okay, and that happens mostly in the capacitive circuits, that current leads by 90 degree ideally. Similarly, if we see the third figure, we can see that voltage is leading, because the moment the voltage has reached to this point, then only the current is starting its value from 0. So voltage is leading, or we can say current is lagging. That normally happens in an inductive circuit also. Then the next important thing is average value. Now if we talk about sinusoidal signal that is available here, we can see that the area being covered under positive half and the negative half is exactly same. So if we have to find the average value, that average value will come out to be as 0 for full cycle. Now the concept of finding the average in the sinusoidal signal is calculated with the same concept as we use for the normal average calculation. Okay, suppose there is a student A with 3 subjects. In 3 subjects he is getting marks out of 50. Out of 50 the student is getting marks 30, 40 and 45. Now we want to find the average. So what we do, we will first of all add everything and we will divide it with the number of observations 3. In the same way, if suppose we are having area under the curve, then how will we find the average value? So we have to use the same formula, total area under the full cycle, then the length of the cycle. Okay, so this is your length of the cycle, this is the total area, right? So that formula if we apply, then this will be the general formula to calculate the average value. Okay, although in the sinusoidal value the value remains to be 0, but if we look at some other diagrams like full wave, half wave, so you can see here the value will not be 0. Okay, so you have to find out the value. So we can use again this general formula and you can get the values. Okay, so in these calculations the derivation may not be important, but what are the final values that can be asked in the MCQ part, so you can expect such kind of questions. Then the one more thing is the RMS value, that is the root mean square value. So the root mean square value of an AC is defined in terms of direct current DC. So if you will see the figure, there are 2 things given. In the first figure the voltage given is DC, in the second figure the voltage given is AC. Then we have certain value of R that is producing some heat. The value of R in both the cases is same, and we are using a wattmeter to measure the amount of heat that is being produced. And then we are saying that RMS value of AC is given as that steady DC current. So RMS is defined in terms of AC, in terms of DC, alright, which when flowing through a given circuit for a given time produces the same heat as produced by the alternating current when flowing through the same circuit for the same time. So that particular value of the voltage when the heat produced in both the circuits across this resistor will be exactly same. So that time the value of this E will be counted as the value of the RMS value. So this is the definition part theoretically. Now from the formula perspective, we can find out the equation for the RMS by applying these three steps, because RMS stands for what? Root, mean, square. So these are the three steps. We are having root, we are having mean, we are having square. So what we are doing, we are generally starting with some value of Im, like I is equal to Im sin omega t. We are starting analysis of current. We can also start with the voltage equation. So it was our choice, we could have started with anything. So here we are starting with the voltage. Okay, then we are applying first step, squaring on both sides. So I square is becoming Im sin omega t whole square, like this. Then we have to find the mean. So mean, I told you, total area by total length. So we are applying the formula and we are applying it for this particular equation, and we are getting equation like this. Now sin square omega t is being converted as per this formula, 1 minus cos 2 omega t over 2, and then we are using simple integration rules, and that leads us to Im square over 2. So I square is Im square by 2 after step number 2 being completed. Then the last step is root. We are applying root on both sides. So once we apply root on this side, square and root gets cancelled, and similarly once we apply root on this side, then it becomes Im upon 2. So this is the very important equation of RMS in terms of current. In the same way, we can also say Vrms is also equal to Vm upon root 2. So what is Im? It is the peak current. What is Vm? It is the peak voltage, right? In the same way, please calculate the RMS values for half wave and full wave. Take it as an exercise and remember the values that you are getting at last. Now the last thing we will be discussing is two numericals based on AC analysis, the type of question that you can expect maybe in the numerical part. Suppose we have a sinusoidal signal given. So we are being asked to find certain parameters like amplitude, phase, frequency, period, angular frequency. So what we have to do in all these cases, you have to always equate this equation with general equation, which can be suppose Vm sin omega t plus minus phi. Okay, and it is not specified whether the question is talking about the current or the voltage. We can also assume it to be Im sin of omega t plus minus phi. Okay, both the things can be applied. So now you compare, this value is what? Amplitude only. So we can directly say that amplitude is nothing but 30. So first part is done. Phase, now again if we compare, we can say this value that is given here is phase. So phase is how much? Minus 75 degree. Then third point, angular frequency. So angular frequency omega. So you compare, what is omega? It is 24 pi. So we will simply apply value of pi. So it will come out to be 12.56 radian per second. Then we have period. So period means time period, and time period is what? 1 upon frequency. Okay, but both the values are unknown to us as of now. So what we can do is, we can also write that time period is equal to, or you can write fifth one, frequency is what? Because omega is given, so we write omega is what? 2 pi f, right? So we can say frequency is nothing but omega upon 2 pi. So omega value is how much? Omega value is 4 pi upon 2 pi. So the answer is coming as 2 hertz. So we first of all calculated frequency as 2 hertz. So time period is 1 upon 2, that is 0.5 seconds. So all the 5 parameters have been calculated, right? So we can move on. Now in this question, we have been asked to find out the various parameters again, starting with the frequency part. So let us see how to find out all the parameters given here. Again, the point is you have to compare this equation with the general equation, that is Vm sin of omega t plus minus phi. So after comparison, what we can see is, so let us start with the angular frequency first. Angular frequency omega is how much? 2000 radian per second. So this part is done. Then we have frequency also. So frequency is what? It will be equal to omega upon 2 pi. So 2000 upon 2 pi, pi is 3.14, so implies that frequency will be 318.4 hertz. Then the third value is instantaneous voltage. So this formula that is being provided in the given question, you simply put the value of t as this value, it will give you the value of this particular time. So what we have to write, V is equal to 0.04 sine of 2000 into t. T is how much? 160 microsecond, then 60 degree. Okay. Now the interesting part is it will come out as 0.04 sine of 0.32 plus 60 degree. Now the question is, can we add these two values directly? The answer is no, because this is in degree and this is in radian. So you cannot simply add these two values together because they are of different units. So we need to convert any one of them. So we can write it as 0.04 sine of 0.32 into 180 by pi, which will convert this into degree. Alright, so it will be now 0.04 sine 18.3 degree plus 60 degree. Now it becomes an easy question. You can now calculate, and the value of V will come out to be 39.16 volt. 39.16 volt. Now is the last part. What is the time represented by 60 degree? Now to calculate its answer, first of all let us understand that what do you mean by time period. We will find first of all time period. Time period is 1 upon f, right? 1 upon f, or it is also equal to 2 pi over omega, which is 2 pi upon 1000. So this value will come out to be 3.14 millisecond. So what does it mean? It means if suppose we had one cycle is getting completed for how much time period? Because time period is the total time taken to complete one cycle. It is 3.14 millisecond. So from this point to this point, it is taking us 3.14 millisecond. But you have also seen that this is how much? 360 degree. So we can also say then, to cover 360 degree, the time required is 3.14 millisecond. So if I ask you now how much time is required to cover only 60 degree, because 60 degree is asked, so it is divided by 6 value. So the value will be how much then? 3.14 millisecond divided by 6. So 3.14 millisecond divided by 6 will give you 0.523 millisecond. Alright, so the value will be what? 0.523 millisecond for the last part. So in this way you can see all the parameters have been calculated, and this is how all the type of questions can be asked from the AC analysis. They can ask you to find out the frequency, the angular frequency, the phase, the time period, the amplitude. Okay, these kind of things can be expected. Okay, with this we complete all the topics from unit number 1. I will be uploading one more video that will include the practice questions based on unit 1. So with this we finish today's video. We will be meeting again in our next video. Till then, have a nice time. Thank you all.